Good afternoon. Thank you for joining us. This is our sixth webinar in our spring 2020 series titled Overburden Challenging Geology, Slurry Injection, Best Practices and Applications. My name is Mike Mazzarese. I'm a senior engineer at AST Environmental. My co-presenter is going to present a case study or project summary at the end of the webinar here. It's Gary Simpson. He's a vice president with AST. I'm based in Denver, and Gary's based outside of Lexington at the AST headquarters in Midway, Kentucky. So I'm sure you guys know the drill, but if you need to ask a question, there's a button off to the right in the taskbar. Go ahead and type that in. We're going to have a Q&A at the end, and we have one of our colleagues is monitoring those questions, and we'll moderate the Q&A at the end of the webinar. So those of you that aren't familiar with how the RPI group is structured, RPI, they're the founders of the technologies that were really covered in the first 4 webinars in this series, detailing activated carbon, and then also BOSS 100, CAT 100, and BOSS 200. All of those are all recorded and are available on the Trap and Treat website that you see there. They also operate what we call our Project Support Laboratory, which was really detailed last week in our RDC focus webinar, or the remedial design characterization. So AST, our firm, we're the national international distributor for the Trap and Treat technologies, and we're charged with project assessment and design as well as QC. And you'll see there we've got we launched a new website a few weeks ago, so please come check us out there. And then the third leg of this stool, the RPI group, are the authorized installers. So AST is an installer. You'll see the project that Gary's going to highlight at the end is a project that AST performed. But around the country and in this country and other countries around the world, we've got a group of authorized installers that have folks that have gone through the training and the RPI group training. They also have very specific injection equipment that we're going to talk about here. Gary's going to focus on it primarily in the case study portion. And here's RPI group footprint. We canvass most of the U.S. and Canada, and you can see there where we've worked in Europe as well as in South Africa, and we'll be working in Puerto Rico this summer. So here's we're down to 3 webinars left in our spring series. Next week is fractured bedrock applications of slurries. We're also going to tie in the RDC that we discussed last week, the high density conceptual site model development. We're going to translate that down into fractured media. So that'll be discussed, as well as best practices and applications for fractured bedrock applications. And we'll wrap up the last week of May. We're going to cover specifically permeable reactive barrier, or PRB, design and installation. So here's just a recap of what we've covered so far in a little more detail. So we talked about the activated carbon-based chemistries, which are going to be obviously slurries. So you see there off to the right, that's what BOSS 100 looks like. That's hydrating a drum of BOSS 100. It comes onto the site under a nitrogen blanket, and that nitrogen is displaced with water before it's slurried and injected. So you can see there, that's why we kind of wanted to break this out as a separate webinar, because slurries can be challenging to inject into the subsurface. Last week we talked about the high density conceptual site model development, more specifically quantitative high density conceptual site model development, and developing models, specifically related to source areas, related to sorbed mass, and being able to really understand the source area architecture, plume architecture, to be able to develop surgical injection strategies. And so that's what we see here. An example where an RDC was performed, the site was carved up into sub areas, and each of these sub areas can be broken down vertically as well, again, to try to maximize where the material goes in the subsurface. Okay, so we wanted to break this out in its own separate webinar, and so the reasons, we'll kind of go over that here is, what are the problems, right? So First off, I said this last week if you were with us, is that everything works in a beaker. So when we're dealing with chemistries on the lab scale, everything works in the lab. And why is that? Well, we know what the specific dose needs to be, and we can really make sure we get good contact. So those things are more challenging when we get to the subsurface. And so the technology needs to have longevity, got to have the right dosing, obviously. Those are really covered in the previous webinars. And then lastly, when we get to the field work, we've got to make sure that we ensure contact. And that's going to be the focal point of the rest of this webinar. Next is, injecting properly is hard. What you don't want to get from your injection contractor at the end of a project is the statement, "It all went in the ground." That's not, we want to make sure we're getting it in the right place. So when you have issues like, we'll talk about surfacing here in a little bit. When you have surfacing issues, we need to go back, and depending on the severity of that, we may have to go back and offset some of those injection points. And so we recommend building in a little bit of flexibility into your budget as well as into the schedule, that in case those things happen, we have the time to be able to go back and make sure we get the material in properly. Next, a lot of designs that we see have really unrealistic expectations with respect to spacing, injectate volume. Everything we're going to talk about here today has been derived from 15 years of field work, of going in and doing hundreds of these sites, injecting slurries into different lithologies, different depth flow grade, different different situations, like gas stations, for example, that have a lot of ground disturbance and a lot of tanks and pipes that we have to work around. I talked about the flexibility already. It's something that we want to make sure that we build into our field plans. And then lastly, direct push is not always an option for our sites. And so we're going to talk about, next week we're going to cover fractured bedrock. Obviously, direct push is not an option there. But what about the sites that kind of fall in the middle? So if you've got a glacial till, it's not going to hold a packer, but you can't direct push into it. What are your options? And that's what we call our pre-drill technique, and we're going to cover that. Gary's going to cover that in detail when we get to the case study part. So here's just a content summary. We'll go through each of these bullets here over the next 15-20 minutes or so before we get to Gary and the project summary. So first off, we talk about liquid injections versus slurry injections. So liquid injections like ISCO and EVO, generally injected low pressure, low flow, high volume. Typically, you can use direct push or injection wells, DPT screens, usually 1 to 5 feet. Injection well screens can vary, but it's not recommended you go anything larger than 5-10 feet, where you're going to potentially get some preferential flow into some high K zones. And lastly, it's really difficult to target low K zones using these techniques, because you're going low pressure, low flow. You can't inject into a clay, for example, at low pressure, low flow. If you're trying to rely on some diffusion-based transport, that can take some time. And if you're using something like chemical oxidation that doesn't last very long, it may not penetrate very far into that clay before the material is spent. So how's that contrast with injection? So, the trap and treat carbon technologies, or ZVI, would be examples of slurries. Higher flow rate, higher pressures. The pressure is going to be dependent on the flow rate primarily. So it's whenever you set the flow rate, it's whatever pressure is needed to meet that flow rate. And one thing and Gary will touch base on this at the end, the pressure that you see on the gauge of the system is not the downhole pressure. So you've got to subtract all that out. So if you see a 500 PSI pressure on your gauge at the system, you may have 400 PSI of system loss. And so your actual downhole pressure would be something like, around 100 PSI. So DPT is generally used. We can't use injection wells for slurries. And we're using usually a jetting type tip. And I'll show you some examples of those shortly when we get to that section of the presentation. And we're really not limited by geology. What's going to change is really the strategy. So your injection point spacing, volume is definitely going to change. So if you're in a sand or you're in a clay, those designs are going to look quite differently, and we'll walk through that here. So here's an example of a site where a low pressure, low flow injection was performed of a competing carbon technology. They didn't do any upfront RDC work. There ended up being a lot of soil mass out there. It was a relatively tight formation. They did low flow, low pressure, and had a limited number of injection points, like, one row of injection points. Probably didn't get good contact. And that was, if you look at the data was highly variable. It had some wells actually even increase, probably due to the amount of sorb mass that was present. And so the RPI group got involved, and we performed an RDC, came in and did a high flow, high pressure application of BOSS 200 into that tight geology. And we had over 3 times the number of injection points and 3 times the number of vertical intervals. And so you can see a clear difference there in the approaches in the data since we did our application. So these are the 4 ways we primarily get material into the ground. So direct push is what we'll really focus on here today, as well as pre-drill. Direct push applications, in permeable to, tight, low K to high K zones. Again, what's going to change is primarily the design, maybe the injection tip down hole. We'll get to that in a minute. The pre-drill technique, Gary's going to really highlight that when we get to his part of the presentation, so I'm not going to really go through that here, but it's really where those are those set of sites where we can't use direct push, but we can maybe use like sonic or hollow stem augers to access those zones and ultimately use direct push. And he'll detail that approach shortly. Bedrock's going to be focused next week, so I'm not going to cover that here. And then lastly, we've got soil mixing, which kind of fits with any in situ reagent, where you can mix it in a tank pit, for example, or you can trench it in if it's shallow enough. So you see there on the right, that's an example of a kind of what a footprint looks like for an overburden kind of standard. This is a BOSS 200 site with the geoprobe and the injection system there. This is actually Gary's pre-drill site that he's going to highlight later on, and that's a sonic rig pre-drilling the direct push locations. These are the packers, the custom packers that we use that are going to be highlighted next week. And lastly, here's an example of trenching in. This is it's a BOSS 100 site in Pennsylvania, where we were putting in a PRB to stop a chloroform plume. Excuse me. So what are the variables when we're looking at design? I mentioned these before. Grid spacing is going to be a function of geology. It's going to be a function of depth below grade. Slurry volumes are going to kind of tie into that, again, depending on the geology and the spacing. Talk about injection tip geometry a little bit, as well as how we can vary injection flow rates and pressures. So the cartoon you see on the right is just a theoretical cartoon of a couple different injection patterns, whether you're in a clay, which is down below, or you're in the sand, which is the shallow unit, and how the distribution looks quite different. So in a clay, we get a much more linear pattern, and up in the sand, because of the fluidization that we'll kind of get to here shortly, you get almost this like propeller type distribution. And I did have on the previous slide that we always inject top down. I think we won't inject bottom up. Top down is really critical for slurries in our opinion, because you're always pushing down into native material, and you can always ensure that you're going to get you have a better chance for horizontal distribution going top down. Bottom up, you're leaving an annulus below you. So this is really probably more important for fine grain sites, where down in this clay unit, if you were to drive down to your total depth, inject in this zone, and then pull up here, say 18, 24 inches, path of least resistance may be back down this borehole. And so we want to make sure that we're always progressing in a top-down manner. So for grid-based design, we're always laying out our grids in a triangular grid pattern where we're offsetting the rows half the distance. So if this is 5 feet, this is offset 2.5 feet. Here's an example of where we would put implants. We'll kind of get to this when we get to the QC section of the presentation, but use these sacrificial implants to be able to assess distribution versus using a monitoring well. And so, as I mentioned, the spacing is to be a function of the depth and the geology, and so it's usually 5 to 10 foot on center for most sites. When we get to PRBs, we're going to do a deep dive on this in 2 weeks when we get to the PRB focus webinar, but just to give you an idea of how that compares to a grid treatment, that's almost always a tight spacing, especially when we're working shallow. Gary's site is very deep, so they were able to go with a wider spacing given the injection unit that they were using. But in general, for shallow applications, we're on a 5 to 7.5 foot spacing because we're trying to replicate what we've done here with the trench, but with injection points. And so if you do 1 row of injection points or maybe 2, you're going to have some gaps there. And so based on our experience, we usually start our designs with 3 to 5 rows of points, and that's ultimately going to be driven by what the mass flux is coming through that cross section. So here's a table of just some example volumes. So these are gallons, what you see there based on the spacing and based on the geology. So if we're on a 5 foot spacing and we're on a clay, we usually, when we go out to start injections, we're starting at about 10 gallons. And then based on what we see, we can increase that a little bit maybe. But you can see that as the spacing increases, obviously the injection volume is going to increase. And then as you go from fine grain to a coarse grain, geologies, sands and gravels, the injection volume is going to increase as well. So here's, I mentioned injection tips, and it's something that AST puts a lot of time and effort into, is focusing on, especially sand sites, where we feel like we have to have a certain exit velocity coming out of our injection tips. So if we have a known flow rate and we have a known total area of our injection ports, we can back out what that exit velocity is. And so we have certain targets depending on the different geologies. So if you look at the figure there on the left, those 1.5-inch diameter rods, so you've got the one on the right is kind of what I would consider more of a standard in the industry. It's a 4-hole 1/4-inch pressure activated injection tip, kind of off the shelf. Compare that to one on the left where you've got 6 5/32 holes. And so when you work out what assuming the same flow rate coming down through those injection tips, you get 40% greater velocity coming out of the one on the left versus the one on the right. So the one on the right might be something you would use maybe in a more fine-grained environment, but in a sandy situation where we need a higher exit velocity, we would probably use something similar to the injection tip on the left. And so we try to go out to our sites with a whole slew of different geometries to be able to match the geology and the site to the injection tip. And the injection tip that you see there on the right is the one that actually Gary's going to highlight whenever he gets when we get to his part of the webinar here. And there's an example of what a soil distribution core looks like for a sand site. And so you see this about a 5-inch seam of carbon, dark carbon here in the middle, and we've got it grayed out maybe 3 or 4 inches on either side. So the total influence vertically here is about 12 inches or so. So for pressure signatures, this is part of our QC program, and I'm sure most of you have seen these. So if you're in a clay, and you can't inject into clay without fracturing, and so you see you have your fracture pressure, and then it's going to drop down to some lower pressure. That's going to be your propagation pressure. These are really important from a QC perspective when you're in the field, because if you're out in a clay and you're working adjacent to a tank pit, for example, it's going to tell you a lot about what's going on in the subsurface and whether or not you're putting material into that tank pit. And here's an example of what a core looks like for clay site. So here's the cross section where you see a pretty good distribution of activated carbon, and here's it in the cross section. From a sandy sites are going to be a lot different from a pressure standpoint, where you're going to have the pressure increase to a certain point, and then it's going to plateau out. And it's kind of hard to see in these photos, but you can see there's kind of similar to that photo that I showed you before. You can see the gray and the black over a pretty broad swath of the soil core here. So from a field QC standpoint, I already mentioned the pressure profiles. We're also looking at water level measurements. You can do that with a water level meter, or you can use transducers. Implants are very helpful because they're sacrificial, so we can put those out as we go. So if we're doing a PRB, for example, we can install implants along the length of the PRB, say every 20 or 30 feet, and that way we're verifying distribution from a QC perspective as we go. And then lastly, as I've shown you already, we frequently take soil borings and cores to be able to look for distribution in the soil matrix. So we worked on a large, there was kind of an R&D project where we did a large post-injection soil core program. And this is kind of special. We obviously don't do this on every site, but post-injection, we collected 40 soil cores, and they were all inspected for carbon distribution. And then as an aside, we also replaced all of the monitoring wells that were on site that were impacted with activated carbon. And then we installed 28 nested wells as well to be able to get greater definition or a greater density of the groundwater sampling. So the figure that you see on the left, so that's for each 2-foot interval that you see at the bottom. That is at least one observance of activated carbon in that 2-foot interval. So you see it's about a 65 to 80% of the soil cores that were collected had at least one activated carbon observance in that 2-foot section. And there were many of these had more than 1, 2, all the way up to 5. I'm just showing the one here. And then what's interesting also is when you look at the total observations of the 40 soil cores, only 3% of those observations were up in the 0 to 6 foot zone, which was above our injection interval. And you look at the 6 to 16 foot intervals, and you see that they're pretty close. They're all around 20%. There's one at 13%. But that tells us that we got pretty even distribution vertically, and we didn't load up one zone in particular. All right, so daylighting is something that we have to deal with on most projects, not all. The shallower that you get, and the more reworked the site is. So if you've got a site that's had excavation, or we're dealing with fill material, or if you've got a lot of soil borings, then the chances of seeing daylighting material go up. And so what's really important is to make sure that we document where the daylighting comes from at one intervals, approximately how much, because then again, we can use that flexibility that we've built into our scope of work to be able to go back and re-inject those areas. And so, how do we manage daylighting, or how do we limit it? So first off, we want to perform a pilot test to make sure that we've got our volumes down, we're getting the good distribution that we need. If you do have to skip intervals, sometimes we have to do that, but just make sure again that it's logged and that we can come back and we can offset at a later point. What we don't recommend is just doubling up on the next injection interval below. Moving around helps quite a bit. Don't overload one area, so skip injection points or skip rows, and then just sort of work your way through the site. And then you can obviously just modify your injection flow rates, volumes. But if you change the volume too much, then you may have to change your spacing. So something to keep in mind. All right, so this is where I'm going to end here. So this is the summary of the pre-drill technique. Gary's going to go into a lot more detail than what you see here. I'll just mention that we've used this site somewhere between, or I'm sorry, we've used this technique somewhere between 35 and 40 sites in various geologies, or even fill material, glacial till, weathered bedrock, in pretty much every corner of the country so far. And so Gary's site that he's going to talk about is in South Carolina. It's a Department of Defense site. So I'll get that loaded up here, Gary, and I'll let you take over.
Thank you, Mike. Appreciate it. So I'm going to discuss a project that was conducted at Shaw Air Force Base, or actually off Shaw Air Force Base. It was a technology demonstration, and the goal was to test or demonstrate the ability for BOSS 100 to address a distal PC and TC. I just want to thank the team involved, Shaw Air Force Base staff and U.S. Army Corps of Engineers staff, and Spectrum Services Group, who was the prime on the contract, and as well as AECOM and SEDECO, all partners in this, and also South Carolina DHEC. It was a great team. It was truly a team effort to move this project through in the time and in the fashion that was moved through. So thank you to the team. Go ahead, Mike. So this technology demonstration, look at the site map. It was a distal plume of PC and TCE. It's emanating from the base from an old dry cleaning operation that was shut down years ago. The base actually operates on site a groundwater pump and treat system just at the edge of the property, and treats contaminated groundwater. So they're actually stopping the mass from moving, but some had already moved down. We're about 5 miles off the base. The goals of the project was to demonstrate the ability of an activated carbon-based injectate to address the distal plume for TC and PCE. PRB, a permeable reactive barrier application. The two primary phases of the work included plume refinement to update the conceptual site model in order that we could finalize the vertical and horizontal limits of the PRB. That field work was conducted in April of 2018 through October 2018. And then we quickly turned around the final design and came up with a design of 650-foot long barrier, and it was BOSS 100. We injected from 90 feet to 167 feet below grade surface. That work was conducted over a 4-month period from 2018 December to March 2019. That included the pre-drilling that Mike talked about previously. Pre-drilling, where we pre-drilled 130 injection points using rotosonic techniques. I'll get into more details about that, followed by the injection of 60,000 pounds of BOSS 100 through direct push tooling within those pre-drilled locations. And we injected with our high capacity mixing and injection system. The system's capable of injecting up to 280 gallons a minute at 2,000 PSI. Go ahead, Mike. So the plume refinement component, or AKA we call our RDCs. If you look, we installed 3 soil borings, GS1 through GS3, at varying depths from 137 to 173 feet across the length of where the barrier was proposed to go into place. During that, we collected continuous lithologic logging. We did grab groundwater samples in the target aquifer, the upper Black Creek aquifer, each of the boring locations. In addition, we did soil sampling and analysis in the saturated zone of the upper Black Creek aquifer and the aquitard at the bottom of that upper Black Creek aquifer that separates the UBC and the LBC. And we grabbed that at that 100-foot clay. In addition, we installed 5 monitoring wells as part of that within that upper Black Creek aquifer. We did lithologic logging of those, and those were to be used for performance monitoring for the long term. In addition, we did verification testing to ensure that we could drive through the backfilled direct push or the pre-drilled points. And so when we did GS1 and GS3, we went out to those locations, used the same backfill technique that we were going to use for all the 130 pre-drill locations. We were able to drive down to 175 feet depth using our 2 1/4 inch rods. You're looking at a couple of photos. One is GS1 is the soil cores. If you look at the very bottom of the page, just above the sign, the clay to the left-hand side below the sand, that was our target. That was the 100-foot clay. That was the aquitard between the UBC and the LBC. And then that sand that's laid out, that is the saturated zone for the Black Creek Aquifer. Go ahead, Mike. What you're looking at is a fence diagram of the lithology across the site. If you notice, there's actually 2 formations above the upper Black Creek Aquifer that we had to go through, the Lang Sign and the Sawdust Landing. And those 2 were not impacted, and the lower Black Creek Aquifer was not impacted as well. If you look to the right-hand side, you'll see about third from the end is GS1 location. We had impacts there, and we stepped all the way up to over 700 or 800 feet away to the GS2 location on the north end of the property, and did the same type boring, did grab groundwater samples, and that well was not impacted. So we came back to the south because we felt like we had defined the upper end of it. That was one of the goals as part of the plume refinement. We came back down and did GS3, which actually went into the upper Black Creek Aquifer, and we also went into the lower, took groundwater samples at both of those aquifers. We isolated, paced that off as well. And so what we came up with as part of that updating of the conceptual site model was where the length of that barrier. So the gray area is the overall length of 650 feet, and we addressed this 30-foot vertical interval, the bottom 30 feet of that upper Black Creek Aquifer, and then took the barrier down to the top of the 100-foot clay. Go ahead, Mike. So PRB installation included pre-drilling of 130 injection points. These locations varied. It was somewhere between 125 total depth to as deep as 167 feet. Total drilling, we used 2 rotosonic rigs. We did that because we found out, and that was conducted simultaneous to the injection activities. Each of the rigs could do about 1.5 points a day going to those depth intervals, and we could inject 3 to 4 points in a day. And so we ran 2 rotosonic rigs. Actually, Sadeco ran the 2 rotosonic rigs, and we operated the injection system. If you look at the pre-drilling operation, we were required, as I said, we had to case off those 2 formations, the Lang Sign, and we cased off with the rotosonic tooling also in the Sawdust Landing, and continue with 4.5-inch tooling down to the top of the 100-foot clay. And then we did full lithologic logging on 10%. So we had all the lithologic logging from the boring locations. We had it from all the well locations, but 10%, and each row of the barrier had either 42, 43 or 44 points. And so that first row that we did, we would go every third one, and we would actually collect full lithologic logging. In addition, for all 130 injection point locations, we did the bottom 30 feet. We did lithologic samples so we could actually truly target where that 100-foot. So that's the level of confidence that we were trying to achieve, that we were putting the product where it needed to. And then once we were at the bottom of the borehole, using the rotosonic tooling, we would backfill the bottom 70 feet of the pre-drilled point with pelletized bentonite, and then as we're extracting the tooling, and then from 70 foot and up, we would backfill the borehole with a 30% bentonite grout. And you're looking at a photo of one of the rotosonic rigs on a pre-drill location. Go ahead, Mike. Then as far as the installation of the PRB, we ended up injecting 60,000 pounds of Boss 100, Not really going to get into the design. Well, how it's 60,000 pounds, that's going to come when Mike talks about the PRB locations. If you want to send me an email, I'm more than happy to discuss that. But it's essentially the mass flux going through the barrier with, and what is that contaminant flux, is how long is that barrier going to last. Boss 100 is an abiotic process, so it's an iron that's impregnated onto activated carbon. So the life of the barrier is how long can that iron treat. It's a function of the mass contaminant. We injected 60,000 pounds across this 600-foot regime, and the 130 points. We used a top-down injection technique. You can see in the photo right there, there's the rig, and they're driving 2 1/4-inch rods. These are one of the points. If you look at the stakes around them, those are completed points, and they're on a point where they're driving down to the total depth. At the southern end of the barrier, we injected anywhere from 90 to 122 feet, and up in the northern end, we were somewhere between 135 and 167 feet on the northern. Go ahead, Mike. There's a couple of photos in there. So this is a picture of the 7822 direct push rig with the injection hoses leading out to it. We're injecting Boss in the orange hose, and the darker hose is blue, and that's where we flush with fresh water across that. Go ahead, Mike. One more. And then now you're looking at the injection head right at the direct push rig where we're driving those rods down. The other thing that Mike's showing you, this is an excerpt from our injection table, and Mike kind of discussed this. If you look, this is injection point 103 of the 130 points. You can see the time and date we injected it. If you look, you see an injection pressure. That's the gauge pressure that you're reading there at the discharge of the pump. It was 640 psi. But then what you see at that first interval, you see the internal system pressure, which is above, is 400, so you subtract that out. So what the subsurface was seeing was anywhere from about 180 psi at these depths to 240 psi. We were looking to fluidize that regime. That Upper Black Creek aquifer is what I will call it is a beach, looks like a beach sand. It was a fine sand. And so if you look at those, we record those injection pressures. You can see we injected 100-gallon shot in this point, and then we also 30 pounds of Boss, so we were at about 0.3 pounds per gallon. And then those are the vertical intervals from 114 feet to 142. You see that injection tip design over there. Mike showed you a photograph of it, and that was so we could achieve at that flow rate of 147 gallons a minute. We were targeting somewhere around 8,000 to 12,000 feet per minute. I would have to do the math with that to see what that velocity was. Once we were completed with the borehole, we backfilled the borehole with bentonite pellets to within 3 feet of the surface, and then topsoil all the way to ground surface. Go ahead, Mike. So these are some photographs. This first photo you're looking at is the Boss 100. Comes in 55-gallon drums. Mike showed you a picture of that. It's under a nitrogen blanket, so the iron doesn't react with the air. You're looking at probably, about 10,000 pounds there. And then you're also looking at bentonite pellets. We use several thousand buckets of bentonite pellets for the project. Next photo. This is in the foreground is a rotosonic rig, pre-drilling a location. In the background, what you see is our high-capacity injection system. It's a Kenworth that's transmission runs our triplex pump. The trailer behind it has 2 500-gallon mix tanks and eductors and shearing nozzle. We actually shear the Boss before we inject it to make it a finer material, and then you see a generator that powers all of our equipment. And then now you're looking at the operator control station on the back side of the mixing injection system. He is in radio communications with the gentlemen that are out there at the geoprobe, and they're communicating on, go to the next depth. Is there any daylight issues? All of those kind of discussions. And so He's also, you see, and right behind him is a tablet where that data you saw a while ago, we record all of that information. So you get that for every one of those points that you inject, 131. You've got, for every vertical interval, you got 5 pieces of data. You got 15 vertical intervals in 130 points. There's tons of data. We know more about that site than what we did way before we started. Next photo. This is hydrating a drum. Mike already showed you one photo of it, but this was on that mixing and injection system. In the foreground, all of our pumps, we have variable speed drives so we can play with the injection flow rate. So I mentioned that we operated at 147 GPM. We can adjust that as high as 280. Go ahead, next picture, Mike. This is the finished product. You're looking from north down south, and that's what the site looks like once we're done completed injection. We've regraded, and then they came out and surveyed all the points. Slide. And so what you're looking at, this is just cut this out of a drawing. You're looking at the colors underneath are the PC and TC plumes, original plumes. If you look, barrier are the red dots in the middle, and then to the left-hand side are the down gradient. Groundwater is flowing from the lower right-hand corner to the upper left-hand corner, and so MW39, MW38, 37 are down gradient wells. 36, 180, and 235 are up gradient wells. The numbers beside underneath the wells, the one on the left is pre-injection data. The one on the right, the white background with black lettering, is post-injection data. So if you compare MW235B and MW237B, this is data. The post-injection data is from December of this year. Pre-injection is last fall before we injected. And so if you look, you can see we've got about a 50% reduction there. It's not quite as good as you move up, but you got to recognize the seepage velocity was determined out here to be in the 20 feet per year. The down gradient wells are beyond 20 feet. Finished this up in March of last year, and this data was from December. They're going out to do some additional hydraulic studies out there to if we've got variable flux across the site, but the northern portion of the barrier up towards 239 and 238, that was the last part of the area finished. So we're just right now at a year. So we didn't really expect to see this. Like I said, it's preliminary results. We didn't expect to see a significant drop given the actual seepage velocity. So I believe that's all I got, Mike. This one.
All right. Thank you, Gary. So I'll invite in Derek Pizarro, who's been monitoring the questions, and we'll open up the Q&A portion.
Thanks, Mike. Hi, this is Derek Pizarro with AST. I'm a senior geologist with our group. And if you haven't answered a question yet, and we've got a couple here already, but there's a box there under questions. You can type those in. We'll try and get to all the questions through this Q&A process, but if we don't, we'll reach out to those individuals where we didn't cover it and get you an answer. Also, you can see the screen in front of you. Both Mike and Gary and Bob have put up their emails. If there's a specific, especially related to the case study question that you have, please feel to contact them directly as well. So look at these questions. Let's focus on pre-drill. That seems to be the biggest one that's generating questions right now. So there's a two-pronged question for Mike and Gary. How many feet can you pre-drill each day? And what is the smallest or largest site you've completed using this method?
Mike, I'll take at least the first part of it. This site, we could do around 400 to 450 feet a day. And that was using 2 rigs. So it's a function of depth, and it's a function of the lithology itself. So, we've done other sites where we've achieved that, but it's just really on the pre-drilling end. What's it going to take? In general, when you pre-drill on a smaller site, you will likely go out and pre-drill all your points and then start injecting, especially if it's a small site, so they're out of the way. Whether it's an auger rig or it's a rotosonic rig. So, this site was about 450 feet is what we were able to achieve. You
Yeah,
want to address part of that,
yeah,
Mike?
yeah. The second part of that, the largest site is probably the one that you saw. On the smaller side, we did another demonstration on a DoD site in Nebraska that had about 20 injection points, and then I'd done a site here in Denver that was a dry cleaner. It's probably about the same, maybe 16 to 20 injection points. So we've gotten them down to pretty small applications. We did a PRB application in Washington State using this technique where we had a glacial till. Those were two relatively small barriers. Maybe they were both about 50 feet. So we can, I mean, it's more of an access issue with the larger drilling equipment than we usually are dealing with when we deal with direct push. So as long as we can, if you got the access to get that larger rig in there, and they obviously have smaller sonic rigs now, so that would be, I think, probably the limiting factor.
Okay, staying on that topic, what's the deepest that AST has ever utilized the pre-drill method?
You're looking at it. It's 167 feet was the depth of one of our injection points, although we went to 175 feet when we were testing, making sure we could get that deep with a 7822. So I'm confident that we can go 175. We demonstrated out there, and we can go beyond that. It's just a function of your drill rig. How deep can you go with the drill rig? And then whether we may have to change the direct push rig, but I'm confident we can go different. I got one of my geologists who always tells me, your answer is, well, how deep can you install a well, collect groundwater is how deep we can inject. So.
All right. The next two questions revolve around the utilization of bentonite. First is when you're using bentonite, are you vibrating it as you install it in the subsurface to ensure continuity?
For this site, no, we did not. We used actually bentonite pellets, right? That was the spec. Anything that was below the saturated zone, and then our Tremie pipe was our rotosonic tooling. So we didn't extract the tooling and then start dumping a bunch of bentonite down there. What we ended up doing was, especially it was this deep, once we got out of that, the other thing that we did was, from a quality control standpoint, we actually measured as we knew and did bucket counts. We knew in 70 feet, this many buckets would be 70 feet. And we actually continually measured while they're putting bentonite down the sonic tooling. We're sitting there with a tape with a weighted end and bouncing it off the bottom. If you're in a more shallow site, it's required pre-drill where we might not use. And on top of the bentonite pellets, we got above the water table, we actually used a 30% slurry. So we didn't really have that issue, and then we would let it set. It could settle down, so it was very flowable. On sites where it's more shallow, when we do this pre-drill technique, that is, we've got a procedure that's written, but we've never used vibrating. We've got a procedure where you put it in lifts and you hydrate it in lifts, especially once you get out of the saturated zone. And then out there, the Army Corps requires, if you're in a saturated zone, you can't use chips. Now, if you're in a really shallow zone, but the other thing we do is, as we're backfilling these pre-drill, we'll take the direct push rods themselves, and we got what we call a push rod. We'll put it back on the probe, and we'll push. And when we were putting bentonite back in the boreholes, after we inject, we push down into those boreholes so we get that hydrated bentonite or unhydrated and pack it in and then start hydrating so we can ensure we've got it a good firm closure of that borehole.
All right. A couple questions here remaining. Last one regarding the bentonite, though, Gary. How do you prevent bentonite from being pushed into the formation?
Well, if you look at what we're doing, right, we're injecting at a very high velocity. So when, for example, on that one point you saw that I showed on the screen, our first injection interval was 114 feet. So we've got a borehole that was created by the rotosonic rig. We go down, drive back through, get to that vertical interval, and then when we're injecting at 10 to 12,000 feet per minute in that vertical interval, and we're injecting every 2 feet vertically. We did that on this site. So when it comes out, and Mike touched it too, you can call it jetting. We're running at a high enough velocity to fluidize that regime. So where we were injecting, the borehole was a 4.5-inch borehole. We're at 2.25 inch. So in reality, you only have an annulus around it of a little over an inch. Well, if I'm injecting at 11,000 feet per minute and I got 400 psi of loss, a lot of that loss is across that tip, but it's because we're jetting it out. So it's not a large screen that we're injecting over. It's a finite vertical interval. So we're jetting through that. So it typically isn't a problem. And as far as putting material, we're not pushing any of that other than that little vertical interval that's, our boreholes or injection nozzles are 5/32. So it's what's ever associated with that cutting through an annulus that's not big at all.
Okay. Switching gears a little bit, this is a two-part question related to sacrificial implants. Could you please explain what the sacrificial implants look like and how they are used? And could you use those at a PRB site?
Mike?
Well, the implants are going to be somewhat of a function of the state that you're in and what you're allowed to use. I mean, they could be PVC, they could be PEX tubing. We've used both. I've actually used on one site we just used a hydro punch. So we were using a hydro punch, at varying radii away from injection locations to be able to assess distribution. The nice thing about the hydro punch is that it's not any sort of temporary well. Depending on the state you're in, sometimes if the well needs to be permitted if it's in for a certain amount of time, and so there's a couple different ways that we can do that. And then absolutely they could be used in a PRB situation. So you could run those down every X feet. So if you've got a 100-foot PRB, maybe you're doing them every, say, 20 or 25 feet to assess distribution as you go. I don't know, Gary, if you want to add anything to that.
Well, it's you're creating a micro well. So you create a sand pack around it, unless you're in a sand soil, and you may create a bentonite seal. And if you're doing what you talked about earlier, Mike, the nested implants or nested micro wells, you're actually targeting different vertical intervals so you can verify distribution within those different vertical intervals. In general, we'll use them before you inject to see if there's a variation in contaminant mass across the vertical interval. So it's essentially just a micro well. And like you said, a PRB aerial treatment, we really like them because it allows you to grab quick and dirty groundwater samples. It allows you to look at water quality changes. Are you seeing black water? Are you seeing silty material building up in them because you're putting so much energy in the ground? So they're a really good tool. But like you said, individual states vary on what they will allow you to call a monitoring well. We don't call them monitoring wells.
Okay. Well, I want to respect everybody's time here. There's a few questions we didn't get to. Some are related to chemistry, which we've covered in previous webinars, and we'll reach out to those individuals directly to answer those questions. Just as a reminder, next week we'll be doing a fractured bedrock webinar, same time, same channel. And the following week we'll also be doing the PRBs that Mike mentioned. I just wanted to say to both of you, thank you. And Mike, the floor is yours.
Thanks, Derek. Thanks, Gary, and thank all of you for your time. I know it's all precious. Hopefully, next time we get a chance to do this, it's in person. So everyone, stay safe, and thank you again.